Hi, everyone. Thank you so much for joining our webinar today on some IP or Scalable Service Oriented Middleware over IP. We greatly appreciate your attendance and continued support for our company. Our host today is Colt Correa, and he is the Chief Operating Officer here at Intrepid. If anyone has any questions throughout the presentation, feel free to use the Q&A feature or the chat, and we'll try to answer as many of them as we can before we finish. This webinar is being recorded and we'll be posting the video on our socials as well as sharing the presentation slides. So make sure that you're following Intrepid on all of our accounts so you can access those resources. Thank you all again. And without further ado, here is Colt.
Okay, I'm just gonna try to find my chat here. So if you have any questions going through this, I'll try to monitor chat. Maybe Jordan, you can let me know if I missed something. And we'll go ahead and get started. So anybody that wants to connect with me on LinkedIn, I have my LinkedIn, I can find my mouse, here we go, LinkedIn right down here. And I am one of the authors of the Automotive Ethernet book, and we're going to be covering one of the chapters in there, which is basically on some IP. So let's go through it. So some IP, as Jordan said, stands for Scalable Service Oriented Middleware over IP. It's defined within AUTOSAR, but AUTOSAR is not required. And as the name suggests, IP stands for Internet Protocol. It does run on top of IP, and specifically it runs on top of UDP. So in some IP, there are, there's a payload, and if the payloads can be kept to less than 1,400 bytes, and UDP is recommended over TCP, and TCP isn't specifically not recommended because TCP has timeouts and connection mechanisms with a three-way handshake that the timing parameters on that are not conducive for real-time control. So UDP is just fire and forget, and with the 1,400 byte payload, you can keep it down to a single frame, which is very reliable on a small Ethernet network that we see inside of automotive. So that's what's recommended. And if you need payloads longer than that, there is what's called some IP TP, transport layer, which is a very light transport layer, in some ways similar to IP or TCP, but without the complexity and without the timeouts and such. So as I mentioned, some IP runs on top of IP, and it can be either IPv4 or IPv6. We see both implementations. It does leverage unicast and multicast capabilities within IP. We'll talk about that when we talk about service discovery. And essentially, it provides a mechanism for communication of different control system components across the network in exchange for relatively complex data structures. So the reason why some IP was originally created, one of the reasons is because in more modern control systems, the complexity of the data that's transmitted over a network is increasing, has increased, where we have nested structures, nested arrays of structures, and so forth. And the traditional networks that we'll call them legacy networks, like control area network, FlexRay, those networks essentially were designed to transport relatively simple signal-based data, and I would even call it scalar-based data, meaning just some scalars like engine speed or temperatures and so forth. And they were never really designed for complex data structures to be transferred over a network, and they don't also to have the speed or the bandwidth necessary for that. So in comes some IP on top of Ethernet, and then also on top of Internet Protocol, to give us a lot more capabilities in what we can transfer from a complexity standpoint, and also because we're using Ethernet from a bandwidth standpoint relative to legacy networks like CAN and FlexRay. And we've really seen some IP increase in popularity because a lot of the newer based network architectures are being designed for software-defined vehicles. And the architecture that's most popular for software-defined vehicles is zonal architecture. And in a zonal architecture, service-based networking that some IP provides is ideal for remote control of a lot of devices inside the vehicle and control over specifically over Ethernet. And that's another sort of correlation between SDV and the use of some IP is the fact that SDV uses zonal architecture. Zonal architecture requires much higher bandwidth within the zone, much higher bandwidth communication methods than compared to legacy networks. And therefore, we see with zonal architectures and SDV vehicles that Ethernet's sort of foundational. It's the base functionality of the entire vehicle. Most communication happens over Ethernet, and having a service-based communication protocol on top of that, some IP, provides a very flexible and scalable communication system across the entire vehicle. So we see a lot of popularity increase in some IP is linked to a lot of also what's happening in the industry with SDV and zonal architecture. So in a zonal architecture, we're going to be using this as the example as we move forward. We have different zonal controllers in the vehicle, and as much as possible, the actuators and sensors become as non-intelligent as possible with the least amount of software, sometimes zero software. And we want to make all the decisions inside of what's called the central compute module. And those decisions will be made in the central compute module, and the resulting outputs of those decisions will be transferred over the network. So essentially what we're talking about in the zonal or SDV architecture is we're talking about a lot of remote control over a network of different actuators and sensors, and some IP provides this capability really well. So let's go through an example to understand this better. The first example that we like to use is smartphone contact list. So let's just assume that we have a smartphone inside the vehicle, and the smartphone connects to a center console module over Bluetooth, which is not related to some IP. But one of the features of Bluetooth is that you can, the center console often in the vehicle has the ability to consume an entire contact list, a contact list of possible phones, people that you could call on the phone, or companies. And so if we assume that we get into a vehicle, contact list gets consumed into the center console, the center console has the ability to use the contact list directly itself. But not only that, there are often other controls in the vehicle that are even safer to use. For example, steering controls and an instrument cluster. So the instrument cluster, which is directly behind the steering wheel, then will enable, if we were to use that user interface along with the steering controls, potentially we'd have the ability to advance and search through the contact list that's stored inside of the center console in a safer manner, because you're not looking away from the road as much as you are when you're looking at the center console. You're looking at the road, looking away from the road more so than compared to the instrument cluster. So we often see instrument clusters and steering controls have the ability to advance through a phone contact list. And so it wouldn't make sense in this scenario to store the phone contact list in the instrument cluster and then also store it somewhere else in the vehicle, because it requires more memory, and duplicating data doesn't make sense. So what we can do here is we can have some IP where the center console offers a service to anything else in the vehicle. And it could be the instrument cluster and the steering controls could offer a service of a contact list. That could be a service. Please, you can say the service related to the information related to a list of contacts that we can call. So let's move on. This shows the data that we might be able to transfer over some IP. So let's just say we're going to create a some IP service to offer up a contact list. How might that look like in code? How it might look like in code is that we have a enumeration that says what type of number that we're dealing with, home, work, mobile, and phone number itself, which would also be the type of phone number, and then the actual number itself, and then within a contact, that could be also structure, which is first and last name, and then a phone number, which is an embedded structure here. So here what we're seeing is that we have some character arrays, for example, inside of a structure, and then in this structure we have another nested structure, and then we could have also another outer structure called phone contact list, which contains a number of contacts, and then an array of contacts, which is an array of structures. So in this particular example, we're showing some of the complexity of the data that we can transfer over some IP. And this data should be obvious that it's generally more complex data, longer amount of data, more data itself in terms of bytes than what we would typically see on top of a controller area network or flex array network. So this is something that we would typically find inside of a vehicle equipped with some IP and Ethernet and one common service. We'll get into what a service is in a little bit when we talk about that. And can transfer this slide is just to demonstrate what kind the relative complexity of data that we can transfer over a network with some IP. Another example could be a radar system. Oh, forgot to explain another scenario that makes some IP also beneficial. Within some IP, we also have the concept of the services can be discovered, services that are functional can go away, and on a dynamic condition based on the circumstance or the environment of the vehicle. So the example we like to use with this phone list is, let's say that we removed the phone from the vehicle. All of a sudden the phone's not there. You forgot it in the restaurant. Then you don't have a contact list. And in that case, some IP offers the ability with service discovery to say, hey, I don't have this service available anymore. Or if someone asks for it, it just say it doesn't exist or is currently non-functional. So some IP has built-in capability to enable the communication system to adapt to dynamic situations. Another example would be, let's say that a new phone came into the car, a second phone, and that second phone has a preferred phone and a different contact list than the first phone. It's possible that the second phone we can replace the existing phone contact list with a second phone contact list, and then all the electronics in the vehicle can be automatically notified saying, hey, there's a new phone contact list here that we can use, and let's reset all of the user interfaces relative to the phone contact list in the vehicle. So it kind of demonstrates the dynamic nature of the way control systems work, especially control systems like the instrument cluster that have user interface directly with the users, the drivers and the passengers in the vehicle. A lot of dynamic nature happening there, and some services may come and go based on those dynamic conditions. Another example would be the radar system in a vehicle. We see some IP supporting radar communication pretty frequently. And with radar data, we often have forward-facing radars. You might have rear-facing radars as well. So you might have multiple radars, and then between a radar sensor, which is generally a pretty complicated device that does a lot of computation, can send out radar data to the central compute module. So in this particular case, we have the producer of the data would be the radar modules, and then the consumer of the data in this particular example would be the central compute module. So you can see that the structure here is that we got a couple radars forward-facing and rear-facing, and then these radars are then connected to a central compute module over Ethernet, and specifically through Ethernet switches that exist inside of the zonal controllers. So I should also note that the fact that some IP is supported with Ethernet, and Ethernet is a very dynamic and type of network where you can add and remove switches, add and remove legs, the addressing of all of the messages, the addressing with IP, the addressing with a MAC address stays the same. So one of the nice things about Ethernet is that the addressing and routing capabilities that are baked in at the media access controller level with MAC addresses, as well as IP addresses, if you're using IP like we are here, are all built in to the system and built into a system in such a way that a minimal to no software changes are required to change the messaging structure or the addresses of certain modules. So this is the reason, some of the reasons why automotive Ethernet as well as some IP have gained in popularity because of the flexible nature of the how you can employ them in a flexible way from an architecture standpoint. And just like the phone example, this radar example will have some relative complex data. In this particular case, it's a structure. Whoops, it's a structure of we might have a sensor ID, number of objects detected, and then for each object, you might have a range, velocity, angle, and maximum number of objects. That could be some information that the radar system going to transfer to the central compute module. Often the radar system is designed to detect objects, so this could be an array of objects that this system has detected either on the front end or the back end. And another example of relatively complex data that can be transferred and sent over Ethernet using some IP. And a third example, which will go into more detail, we actually have this example written into code for Linux-based system for our RAD. We often come to customers' locations and we do training on site or training here. And then part of the hands-on training that we do is using our Neovi Pi, which is just a Raspberry Pi that is in an enclosure. So we have software and a demonstration system that demonstrates this real-world example of a mirror service for some IP. In this particular example, we have a right mirror module, in other words, an ECU that controls the mirror, whether it's folded and the exact position, how it points backward. And we also have a user interface here that's connected to the central compute module. And in this user interface, we have some buttons so the user can adjust the mirror position. So in our example, we'll have a way for the right mirror module to provide a service information relative to the mirror position and a mirror fold, as well as offer capabilities to adjust the mirror module. And the central compute module will offer a service of the status of the buttons that the user interface will use to adjust the mirror position. So in this particular example, we have some services offered by the right mirror module and some services offered by the central compute module connected to the user interface that will adjust the right mirror module. And of course, we're just showing the location of the ECUs that are affected in this example. And we could easily use the other mirror module and other mechanical things that happen in the car. But in our example, we just like to use this right mirror module because most people are familiar with that, as well as it's a good, it's just a very common way of controlling the right mirror module. And this is loosely based off real world examples of some IP applications that we've seen. Okay, so before we get into the details of the protocol itself, just to mention that the most recent version of the protocol as defined is in AutoZAR. And as I mentioned before, AutoZAR is not required. Some IP was created outside of AutoZAR, but AutoZAR brought it into its umbrella of a lot of different specifications, and the most recent specifications for some IP are defined within AutoZAR. And there's 4 different documents. One is the protocol specification that defines serialization examples, message format, which is the most important, which we will cover, how to do things on UDP, some error handling. Then we have a separate document that describes service discovery. So in some IP, one of the things that we can do is we can discover services dynamically, and that's in the optional part of the protocol which is called service discovery. And I say it's optional, but I've yet to see an implementation of some IP that does not use service discovery. So most implementations that I've seen of some IP have service discovery. But that's the second document, second specification. We're going to go through all of these briefly before we conclude today. The third one is transformer. Transformer defines how do you take the memory of an ECU, like a structure in memory of the ECU, transform it in a way that it can be sent on a wire format, and then take that serialized format and unserialize it and put it back in the memory of the target receiving ECU. That's what a transformer does, and some IP has a transformer that we can use that defines how to do this. And I briefly mentioned the some IP transport protocol. Some IP transport protocol is the protocol that we can use. It's a very lightweight, very easy to use protocol to transport more than 1,400 bytes in the case of your in the case where your payloads on some IP need to exceed 1,400 bytes. If your payloads do not exceed 1,400 bytes, then it is recommended that you just use straight UDP. Fire and forget. A single frame of UDP can carry up to 1,400 bytes of some IP traffic. If you need to go larger than that, then we can use some IP TP, which is some IP transfer protocol, to transport more bytes than 1,400. Often some IP is used together with AutoZAR, and just to mention that the one nice thing about some IP is that if you're familiar with AutoZAR and how PDUs work and PDU router, all of that stays identical. It's exactly the same. And just to put a plug in for one of the things that we sell, we do sell a tool that that enables you to edit and create AR XML files. So we see with some IP, with AutoZAR in general, whether you're using Ethernet, whether you're using CAN or FlexRay, the industry has moved towards what's called a database format for tools that Intrepid supplies. And the database format that is the standardized one is AR XML, AutoZAR XML file. And this is where we would store in this database all of the information related to some IP, who are the IP addresses for different ECUs and the service providers, who are the service consumers, all of the information necessary, including transformer information. How do you decode PDUs? How do you encode them, and so forth, is contained in an AR XML file. And our tool to edit and to create AR XML files is called EEACon, and you can see the link here for more information. Okay, so we've gotten this far and we haven't even defined what a service is. Some IP can be defined as a service-based communication protocol. And a service is essentially just a vague concept that includes a service is the combination of any 0 or more of events, methods, and fields. And these are very easy to understand concepts, but they're also very flexible. An event is anything that causes data to be sent across the network. So event could be when the doors open. An event could be a periodic timer every 10 milliseconds. An event could be when a phone goes inside of a vehicle to consume a new phone list. An event could be the radar system detecting a new object, an event of detecting a new object, or an object is removed. So anything you can think of that might trigger data to be sent across the network is what's called an event. A method is something that happens inside of the ECU, the operation of the ECU. So we can, for example, remotely call a method. For example, in our mirror module example, we could potentially call a method that moves the mirror up or folds the mirror. Any actions that the ECU can do can be with methods can be controlled remotely across the network from a remote ECU. So that's what methods are. Enables a specific ECU to offer capabilities that ECU offers, and to be controlled remotely through a remote procedure call. That's what a method is. And fields are the data that we want to send itself. So these are our structures, as we mentioned. That would be a field, a contact list, radar data, positions on the mirror module. Those are all examples of different types of fields. Fields can be very simple, scalar, to all the way very complex, nested structures, nested arrays of structures, and anything that you can think of. And fields optionally have notifiers. Notifiers send new updated information on change. Fields can have getters and setters so that you can set and get the value of a field remotely as well. So service is just a combination of any of these three things. And that's how we group together this protocol. It's a service-based protocol. So there's different terms. I think we've covered most of them here, so I don't think we'll go through. We won't spend time going through this list. I believe we've covered most of them. Service, we just covered what a service is. A service instance is a single instance of the service. There can be multiple instances, like in our particular example, you could say one instance is the right mirror module, and the same service could be an instance of a left mirror module. Any service provider can offer a service, stop a service. With service discovery, you can find services, and an event is a group of anything that triggers data to be sent. And we talked about fields and different events. So we'll move on. So as an overview, there are ECUs inside of a vehicle and electronic control units. And with some IP, there will be consumer ECUs and provider ECUs. Should be pretty simple to understand that a provider provides a service or multiple services. Consumers consume services from other ECUs. And should be noted that any provider can also be a consumer of different services, and a consumer can be also a provider of different services as well. So the basic network type is that you have ECU A, ECU B. A is a consumer, B is a provider, must be assigned an IP address with a port. There can be two different ports, one for service discovery and one for application point-to-point communication. If we are using service discovery, it is required that there is a multicast address space. So if we are using service discovery, then there will be a different IP address, Internet Protocol address, either IPv4 or IPv6, that is a multicast address space that would enable all ECUs in that within that domain, that some IP domain, to communicate to each other. Okay, types of communication. There are really just three types. Method call is essentially you just call a method in a provider ECU, and there may be a response, or there may be just a fire and forget where there is no response. Those are method calls. Getters, setters of fields essentially just send a UDP message from the consumer to the provider, and you can say get or set, and the consumer then can either set the parameter, which could be a complex parameter again, complex structures and arrays and so forth, and then the provider then will send the result, the optional result. The result again can be complex. So that's simple method call to create method or to invoke some functionality inside of an ECU that may have a response or not. Getters and setters will get and set data inside of the remote ECU. And then the third type, there's two types here: event notification and field notification, but if you look, they're identical, they're the same. So in this particular case, we require service discovery. Service discovery, part of service discovery is to subscribe to an event group, and the subscription to an event group then will give the consumer that subscribes to the event group inside of the provider the ability to get notifications, event group notifications from that event group whenever the event for that event group fires. So the way it works here is just let's just assume you know about the service already in advance, and then ECU will say, I want to subscribe to this particular service that this provider offers. the provider then will send a response service discovery acknowledgement that things did go as function, did go well, and everything in a good result. And then from there, the provider will automatically send event route notifications to the consumer IP address. This is all based on IP communication from the provider to the consumer whenever an event group notification happens. And again, this data can be complex data. And field notifications is the identical thing. You'll see in even the headers, the numbers are all the same. So these two are the same, even though they're named differently. Okay, let's move on. Gonna take a quick drink here if you'll allow me to. Okay. So here's a example of some IP network or let's say an Ethernet network that supports some IP. We have 5 different ECUs. And if we're going to use service discovery, as I mentioned, we have to have a multicast address space. So of course, we're using just IPv4 because that's simpler to represent than IPv6. So here's an IPv4 multicast address that has to be baked in, that has to be programmed that way into the system has to recognize this address space. And this is going to be defined inside the ARXML file. And then of course we're dealing with IP addresses and UDP communication. So we also need a port. You got to have for UDP communication, you got to have an address, IP address, as well as a port. So we have that. So that just means that when this network boots up, any of the ECUs here then can communicate on this address space to find or to publish the services that you offer. And so we'll get into more of that when we talk about service discovery. But just to let you know that this address space is required. And then also on this slide, we're showing that there can be a different multicast address space for data to be transferred. So it would be theoretically possible for one of these ECUs, let's say the front camera, to offer a service of camera data and send that out on a multicast address space. You could send the data, the event data, out on a multicast address space, and that potentially then would enable more than one ECU to receive that data. That's what the multicast enables. If you're not using multicast for data, then it can be just simple unicast addresses, which most some IP communication is simple unicast addresses, but it's not required to have all unicast addresses. So we can have a multicast address space for communication on some IP as well. But to note, every ECU needs its own unique IP address, and there has to be a port associated with that so that you can have point-to-point or unicast communication between ECUs once you offer or subscribe to a service. Okay, so let's go through our example here, and hopefully everything comes together. So again, we have a central compute module inside the vehicle. We have a user interface that enables the customer or the driver of the vehicle or the passenger to adjust the mirror, the right mirror module. Inside the right mirror module, we have a mirror status service. These are just names here. So the button status service is a service that offers information about the button user interface that the user uses to adjust the mirror. The mirror status service is a service that offers information and control of the status of the physical mirror itself. So the position of the mirror as well as whether it's folded or not. And so this is a very simple but very hopefully comprehensive example of how things work. So with every service, you have to give it a service ID and you have to give it an instance ID. We'll talk about the structure in a minute. And within this, so the button service status is this service ID, globally unique within the some IP space. And then a mirror status service also has to have a service ID that's uniquely identifiable, that's unique in the global space of the some IP domain and an instance ID. And then we have event groups. So some of the event groups like mirror button status, this event group would fire potentially whenever a user would push the user interface to adjust the mirror. And that's the event group is just a number essentially that defines an event that gets fired or is triggered based on some condition. In this particular one, it's whenever the mirror button status changes. In the mirror service status, the mirror fold status is an event. So in other words, if the mirror gets folded for whatever reason, then that could trigger an event group, a notification of this event group. And then we have fields. Fields, like I said, that's our data. And of course, in our particular example, we don't want it to be a very simple data. We want to show that we can do enumeration structures. So in this case, the fields themselves, the data is our structure. So this is a structure. Its name is mirror button up, mirror button down, left and right. And if we look at what is mirror position, what is the structure button position, it's either on, off, or error. For example, actually, this is just a simple enumeration. And then some events that could happen is a mirror button up button was pressed, down was pressed, left and right was pressed. So these are all different events that then are associated with what's called an event group. And so all of these events can trigger a single event group. And then when this event group is triggered, it'll send out all of the information about the button status, essentially. And on the right mirror module side, of course, we have mirror position. The main field is going to be the position of the mirror. And in this particular case, the way we've defined that, it's assigned 8 X and Y position. And then we have a fold pause, fold position F. So that's what this is as far as the field goes. And then the events will be if the fold position changes or if any X or Y position changes, those could be events. And then we could have setters and getters on that to where you can set and get the fold position, X and Y position for the field that is mirror position. So with these methods, the get and the set, we can actually change the mirror position. So hopefully that's a good overview of all of the things that we're demonstrating here. One service provided by a right mirror module and another service provided by a central compute module, and these two services will interact and work together to provide a whole comprehensive control system. Okay, so let's go on to the some IP header format. The header format, all some IP messages have the same identical header that we're showing here in yellow. It starts with message ID. Message ID is a combination of the service ID for the service as well as method ID. The upper 16 bits is a service ID and the lower is a method ID. So the service ID has to be globally unique within the some IP domain. It is possible to have, for example, one some IP domain on a virtual LAN inside of a vehicle and a different some IP domain that's on a different VLAN, or the networks could be separated. So it is possible to have more than one some IP domain inside of a vehicle, but they would have to be, to avoid conflicts, they would have to be separated in some way, either through virtual LAN or physical LAN access difference. All of the service IDs within a domain in a vehicle have to be globally unique. And then the method ID is 16-bit. And if it's between 0 and 7FF, it means it's actual method call. So mentioned method call could be adjust the mirror position, for example. And if the value is between 8,000 hexadecimal to 8FF hexadecimal, it means that this communication has to do with events or notifications. It is not a method. So that you can get some information about the values here. And then there's some special use case numbers here. 8100 is used for service discovery, for example. So if this method ID is 8100, it means that this message is a service discovery message. So then we have number of bytes starting from the request ID to the end of the message. We show that here. Request ID is a 32-bit number that consists of a client ID and a session ID. Client ID distinguishes the client of the communication. So the client ID is loosely associated with an ECU, but inside of an ECU might have multiple clients as well. So we got to be careful just saying physical hardware is equal to one client ID. That's not always the case. Client ID, particular ECU, especially when we talk about zonal SDV ECU, some of them can be very complex and have multiple client IDs in there. So, but a client ID and then a session ID distinguish between multiple requests from the same client. So if you made 2 requests back to back, this session ID would come back in the response so that you know what response was associated with which request. So you have client ID, session ID, and then we have protocol version, which is currently fixed at 1. Interface version, this is a number that we want to say, okay, in case the version changes, we know it's changed. And then message type and return code. So message type is this table here. It could be a request. It could be a request that's not expecting a result, request no return. Could be a notification. This is our event notifications. Could be a response to a request, or it could be an error. So really, the types of messages that we have are, it's a small number. There's only 1, 2, 3, 4 types, 5 types, I'm sorry, 5 types with error. Request, this would be like a request to subscribe to a message, for example, or subscribe to a service. Request with no return, like a method call, a notification, event notification, some event happened, and then this could be a response or an error. So, and then return codes, it'd be what you'd expect. Okay, meaning everything went well. Unspecified error, and then different error codes that we can have, as you can see from this table. Okay, so that's the basic format of all messages that happen on some IP. And the way it works is if, for example, an event notification happens and you need to pack in some data, the provider ECU will create this header. So in our case, it would put, let's say it's the user interface, user just pushes a button on the screen. We would shove in the service ID and the event ID here, service and event ID that was just triggered, put in the length, the client ID of us, the sender, the provider, protocol information as we just discussed. And this would be a notification message. So this message type would be notification. And then the data, the actual structured data then would go right in the payload. So that's how event notification would work. So that's pretty simple way of communicating. And then we rely on IP addresses and MAC addresses to enable this message to get sent to the right recipient. So now let's talk about a transformer. We did just discuss a payload. So if we are sending data over, as I mentioned, we can have nested structures, we can have array of structures, arrays, any type of complex data that you want. It could be, any length of data, 32-bit, 8-bit, floating, signed, unsigned, all these things. So the question is how do we take all of this structured data and put it in a format that's serialized that can be sent on a single one, over Ethernet in a single twisted pair, and then unpack it at the other end. So that's essentially what a transformer is. And the transformer sets up rules on how to pack things in. So that's essentially what it is. And as I mentioned here before, we went through our button service example. Let's say we got a user pushes a button here. That would be the service ID 20, instance ID 01, and the event could be, in this particular case, on mirror button up, which would be this number. And then in the payload, we would actually have the button position. So this section right here demonstrates the example that I just tried to explain. You can look at the numbers at your leisure after. So in the SumIP transformer, there are many, many options. We could talk about this for a long period of time. I'm going to do a time check here. We only have 10 minutes left, so I have to hurry. But essentially what this does is it says, and there's a lot of different options in which you can use a transformer. So we can transform data just based on data. We can also transform the data, including tags. If we have a tag, this is optional. What we can do is we can have data. This is the actual data. We can tag it with a data ID, as well as format information about what type of data is being transferred. And the benefit of doing tags is that if you upgrade software in one ECU and it doesn't recognize a tag from other ECUs, then you can just ignore them. And if you didn't have tags, then you have to assume that all the data that you're getting is in the right format, in the right place. And if anything, if someone updates software in a different ECU and modifies that format, that means you're gonna not receive data correctly. So there is a trade-off. Transformer with tags is longer, but it makes the software versioning and the structure of the communication loosely coupled so that you don't have to be so strenuous with updating all the software and all the communication in the entire network. You can just update one, and any fields that the ECU doesn't recognize, it can just ignore based on the tag. Now, unfortunately, we're running out of time. I don't have time to go into all the details. I'll have to hurry up a little bit here. We'll go into service discovery. Service discovery is pretty simple. There's really just 6 different types of things that we can do with service discovery. Again, remember that we have a predefined multicast address space. So all these ECUs, if you send into this address space, all of these ECUs will receive it. There's a find service, an offer service, a stop offer service, subscribe event group, stop subscribe event group, and subscribe event group acknowledge. Those are the 6 communication types for service discovery. It's pretty simple. We'll go through one example. So the right mirror module, when it boots up, it gonna inherently know, hey, I'm expecting commands from somewhere to send me what is the user, does the user want this mirror adjusted? So what might happen is the right mirror module will send out on the multicast address, find service. I want to find this service. What service is going to look for? It's going to look for the button status service, which is service ID 20. And then the ECU that provides that service will send out an offer service. And then that gives the right mirror module then the opportunity to subscribe to an event group. The event group could be this mirror button status. And then there's an acknowledgement. And then from there, the device, the central compute that offers the service, will send out notifications whenever the event group that was subscribed to, whenever that event triggers. So this is pulling it all together for our example. And you'll see that it's a pretty lightweight and easy to understand type of protocol once we lay everything out. We don't have time to go into service discovery message structure. I'm really running out of time here, unfortunately. But there is the same header that we've seen before still exists in the service discovery, and then we have arrays of services that we're either going to look for or we're going to publish. And the reason why we have an array, the array is dynamic, is that you can do it with one message. So if we didn't have an array, we'd have to, for every service that we'd want to subscribe to, we would have to send out a new message. And because we have an array, we can say, okay, I want to subscribe to these 5 different services as opposed to just a single one. Of course, a single one does still work. And then when you go to publish services, if you're programmed to publish the services that you offer, then in the same manner, you can publish multiple services that you offer at one time. There's different message structures depending upon what we're doing, either find offer and stop offer, all have the same structure, and subscribe, stop subscribe, subscribe back, and then sub event group act have a different, a slightly different structure here in the what's called an entries array. And this will be for every service that we offer. Again, we don't have time to go into the details because we're running out of time, but it's important to understand that part of service discovery message structure is things that include information about the IP addresses for services. So one of the things that happens in service discovery, remember, service discovery happens on a multicast address space. It does not inherently, in the communication, doesn't inherently tell the system which IP addresses and ports are associated with particular services. Now, that information should be in the ARXML file, but that information can also be dynamically learned through the communication of service discovery as well. So one type of service discovery message is for an ECU to publish an IPv4 or IPv4-6 address, as well as ports associated with specific services, so that the system dynamically can learn what services are available on what IP addresses. Alternately, it could be programmed in the system, hard-coded with those IP addresses. That is also possible, and we've seen both, where it's hard-coded in the system in each ECU, or where the system dynamically finds out in runtime what the IP addresses and ports are associated with different services. And the last thing we're going to talk about, as I mentioned, is the transport layer. And transport layer essentially is a very lightweight, very simple. You'll see here that we have the same message header, as I mentioned before. And if we have a transport layer that is being used, bit 2 of the message type, it's an 8-bit number. Bit 2 will be a 1, will be a true, or will be asserted 1. That's this 2, 20, 21. So you'll see that this is TP request. So essentially what we're doing with transport layer is that we just have a different message type, which we assert the bit 2 equals to 1. And these are just a mirror image of what's already existing without the transport layer. This just enables us to see that this is transport layer communication. And then we have an offset. We're adding in essentially to the message header for transport layer. We're going to add in 32 extra bits. The 32 extra bits, 28 of them is going to be an offset for partial messages that we can reconstruct them, and then some flags for the reconstruction. So you'll see, the only thing that we're doing with transport layer here is very simple. We're adding in 32-bit extra information. 28 bits going to be the offset, so we can combine or reassemble multiple payloads of multiple segments of a longer message. So in this particular example, let's say that we want to send more than 1,400 bytes with some IP transport layer. This is an example of 5571 bytes, and you'll see that in order for this to happen, that we would send out 5 different segments. First segment would be with transport layer, all of them with transport layer flag on. This is the second, this is that bit that I mentioned already. And then we have an offset value. How many, how much into the message are we going to offset to reassemble? And then there's a more segments flag, meaning every single message except for the very last one will have more segments, meaning more segments are coming. And then when we get to the last segment, the last header, we will have all the segments in which we can combine this larger message. So hopefully that was a good overview of some IP. Really appreciate everyone being here. We went through all of the different types of messages and structures that some IP offers, including the basic protocol specification, service discovery, transformer, and the transport protocol, and went through some examples of how you might actually implement some IP So hopefully it's a practical and simple explanation of how you might employ and the benefits of some IP. So thank you everyone for your time.
Before we wrap up, I just want to give everyone a couple more minutes if they wanted to submit any last minute questions. I also shared the Linktree and Colt's LinkedIn profile to the webinar chat, so everyone has access to that. If there are no more questions, we'll go ahead and end it. Okay,
Okay,
great.
thank you everyone.
Thanks, everyone.